Well, thank you, Casey and EarthScope for setting this up, and good morning, afternoon, or evening to everybody, wherever you may be. Yes, it's a pleasure to be able to talk about some of this ongoing research. I'll be talking about some recent work that I've done, but I also want to acknowledge the many other people around the world working in this area, including some of my collaborators listed here. And I especially want to offer a shout out to the world's global seismographic network operators for all that they do and all that they do to curate and manage these data. So sort of a background and context here for this talk. I'm going to talk about this as a manifestation of climate seismology, and by that I mean near-surface seismology in a climate context. And this is a really exciting and growing field where we use elastic waves in the case of seismology to interrogate environmental and climate-related processes around the world. Elastic waves are ubiquitous after all, and we have many opportunities to expand our discipline meaningfully into these areas. So some of the observables that are relevant to the climate change sets of issues include processes spanning the atmosphere, hydrosphere, and cryosphere, some of which I've listed here. And of course, much of this is highly sensitive to changes in Earth's surface temperature, and by that I mean the atmosphere, the near-surface solid Earth, and the oceans. And of course, the Earth is going through a very rapid transition to higher temperatures as our climate changes. And 2023, in fact, was Earth's warmest year on record. So you would expect that as seismologists, we'd start to see manifestations of this in certain aspects of our data. The cryosphere, for example, is especially vulnerable and responsive to environmental and climate change. As you know, in terms of global ice loss and changes in the dynamic processes that produce cryospheric seismicity. Ocean thermal and wave conditions are particularly relevant to climate seismology, as I'll point out in this talk. Oceans, after all, are absorbing about 90% of the energy of global warming and creating relatively rapid changes in the upper and the deeper oceans, and also driving around 1/3 of present sea level rise on average around the world via thermal expansion. The amount of energy here is really astonishing. About 200 zettajoules, a zettajoule being 10 to the 21st joules, are estimated to have accrued in the ocean since 1990. So here are some examples from the relatively recent literature. Wenbo Wu has an exciting set of studies where he's using T phases in the upper panel here to basically thermally interrogate the temperature of the oceans through acoustic tomography. Here's a really interesting study on permafrost velocity and temperature from dV over V, ambient noise inversion, where it's been, in this case, calibrated on Svalbard with temperature data. This is a really interesting example in the lower left here of changing spectral processes in the Antarctic fern layer, as the fern layer, in this case on the Ross Ice Shelf, underwent a period of warming and slight melt, and then a period of refreezing. And here's an early example from some work that Dan McNamara and Peter Ramirski did, starting the process I'm going to play out today of interrogating the oceans for signals related to climate change as manifested by changes in wave energy. So why is the global microseism interesting? After all, for many decades, seismologists viewed it as either a curiosity or an annoyance, and indeed in many of the early records, it was intentionally filtered out, or otherwise efforts were made to remove it. Well, first of all, it is the predominant seismic signal on Earth if you consider it in the absence of earthquakes or other large transient signals. And as seismologists, we should understand its source processes and wave field, after all. It constitutes the background noise field that determines our ability to detect transient and other signals globally in the long period band. It generates a continuous and highly significant global body and surface wave energy field that's widely utilized for correlation-based tomography and structural imaging. And innovative methods are still being developed to use it more effectively for this. And it provides a ubiquitous long period signal that we can use to calibrate and assess instrumentation quality, particularly for instruments that have been deployed for many decades. In a more specific sense related to climate seismology, microseism signals provide information, as I'll discuss today, that's directly relevant to Earth's spatiotemporal wave field and period-dependent wave field. It's continuously observable, regardless of weather, day, night, other complications. So ideally, we have a 1 sample per second or a higher density temporal record of this over many years, extending to decades. It's complementary to and yet independent of oceanographic and meteorological data and modeling, looking at the state of world's oceans. And it's quite temporally extensive, of course, as it extends back 40 plus years for digital data and 80 plus or even a century in extreme cases in the analog data space for monitoring the wave energy on the Earth. So I'll talk about 2 processes today that create this continuous seismic global signal. The largest of these is referred to as the secondary process. It occurs at shorter period, between 8 and about 14 seconds, and it's generated by wave-to-wave interference interactions that generate water column pressure variations that extend all the way to the seafloor. These oscillations have twice the frequency of ocean waves in the case of 2 monochromatic interacting wave fields coming together at 180 degrees azimuthal difference. But it does depend on having this wave-wave interference field, and it also depends on ocean depth because you get an acoustic resonance effect for compressional waves in the ocean column. And so it's certainly the dominant global continuous seismic signal on Earth, but it has the requirement that we have interfering ocean wave fields, and thus frequently 2 interacting ocean wave sources at similar periods for it to be generated. There is a very long period hum signal that's visible globally, but it's very low energy. This is caused by very long period gravity waves exerting forces on the ocean floor. It's more difficult to observe than these other 2 mechanisms. I won't mention it further. And then there's the primary microseism, which is the one you might think of first in terms of how waves couple into the solid Earth. And that's the direct ocean wave energy coupling at the seafloor. And that'll be at depths less than about 100 meters, typically, maybe in long period waves extending to 200 meters or so. And so it's controlled by near coastal proximity, bathymetry, and wave amplitude interacting. So these are the direct forces applied by waves, gravity waves on the Earth. These seismic waves have the same period as the ocean waves. And as I will try to show you today, they provide the most direct seismological proxy for integrated near coastal wave energy globally and have quite a strong signal in that regard. So on the right, there's just 2 cartoons here that show you the difference between the secondary and the primary mechanisms. So the microseism signal in the spectral domain lies between the Peterson high and low noise curves, as shown in this figure. This is a probabilistic spectrum, so expressed as a probability density function. Globally observable, well outside the range of normal noise sources, so it's quite distinct. And the primary microseisms typically about 20 dB smaller than the secondary, but still easily detectable. So you can see that with the 20 dB arrow here on the right. And this is basically an agglomeration of all the data collected hourly by hourly at ANMO, which is a station we'll use frequently in this talk, in Albuquerque, New Mexico. It's the vertical velocity. So a majority of seismic stations, if you look at this signal over many years, show a very clear primary and secondary microseism amplitude variation. So here's a movie of this. These are weekly vertical velocities spanning about 17 years in New Mexico. Once in a while, you can see large earthquakes fly by there, but most of the probability density function mode is centered right along the secondary and primary microseism lines there. That's the mode. And you can see the annual variations here. And this is driven by the increased intensity of storms in the Northern Hemisphere during the Northern Hemisphere winter. And so many of these have a very strong, stations have a very strong periodic signal in their microseism intensity or energy or amplitude. So, of course, the effects of global climate change on the ocean are an object of great interest to meteorologists, climatologists, and oceanographers. And there have been many independent estimates now of this. This is a highly cited paper for 2019 by Reguero et al. That shows both the wave power in the various oceans. You see the Southern Ocean is very intensely energetic in its wave field, as you might expect, and also shows the secular trends here that they estimated for meteorological and oceanographic data. And these trends are not that small, especially when they're accrued over many years, around 0.4 to 0.5% per year in this study. Here's another study that just came out this year, basically doing a generically similar analysis, but trying to get more of a handle on the spatial distribution of increases in wave power. And their observations suggest that most of it's in the Southern Oceans, but it's positive almost everywhere, and it's also strong in the North Atlantic. So this signal, you might think, should be visible in its own seismological manifestation in our data sets as seismologists. And so last year, Adam Ringler and Thomas Lee and Rob Anthony and I developed a methodology to systematically look at these trends and other features within long-term global seismographic network data. And so the first thing we do is we just create a lot of power spectral density estimates for a variety of global networks. We're agnostic about networks. We only care about stations that have been operational in the same place for very long intervals, typically decades to multiple decades. We correct for instrument response. We calculate hourly power spectral density estimates. And we do basic tests for data completeness to make sure that those are accurate representations of the power spectral densities in the microseism band. And we integrate those in 2-second wide bands at these various center frequencies to estimate their amplitudes, in this case, their instrument corrected to acceleration, and their velocity squared power. And we'll use that as an estimate of power that we project back into the ocean wave field. We characterize the annual variations I was talking about a moment ago as a Fourier series, so we can remove the stationary component. And again, everything I'm talking about here relates to the vertical component, and the vertical component data are insensitive to the direction of Rayleigh wave propagation. They're also insensitive to horizontally polarized love waves. So that makes the attribution of the wave field simpler. You might think that large earthquake surface wave trains would obscure the microseism, and of course they do, but they don't really do it for that large a proportion of the time. But we do implement a standard culling process here to remove various hours of data related to how large the earthquakes are, to include, in the case of the largest earthquakes, multiple Rayleigh wave circuits of the Earth and so forth. So it's pretty conservative culling. And we also compare the results of these various power spectral density integrals to the high and low noise Peterson global noise model to look for obvious instrumentation aberrations. That is, super high amplitude signals associated with calibration pulses, super low amplitude data associated with station downtime, and so forth. These culling algorithms typically remove a few percent to about 10% of the data, but they're relative to the things we want to look at in the climate signal, they are random. And so they turn out not to have a large effect, but we look at that very carefully, make sure we're not potentially getting artifacts from these other signals. So we reduce these time series to daily sample, median, amplitude, or energy as our basic time series for further analysis. And then we apply a robust, that is outlier resistant L1 norm minimizing trend estimation procedure to see to first order if they're statistically significantly increasing with time. And then we, again, going back to the data culling process, we validate the robustness of this method by seeing how important the earthquake signals are and occasional non-physical outliers from calibration pulses or station downtime, how much those affect our trend estimates to make sure that we're really certain that we're looking at a potential climate signal here. And to do this outlier detection using the noise model, we basically take 5 times the Peterson low noise model prediction and 50 times the high noise model. I'll show you that in a figure in a moment. So first of all, this is what a raw data set looks like. This is almost 600,000 hourly power spectral densities from Albuquerque, New Mexico. This is the logarithm of the integrated power spectral density in these various centered period bands that are 2 seconds wide. This is vertical acceleration. And you can see immediately how much larger the secondary bands are than the primaries. And this is that 20 dB approximate separation between the bands, but they're quite distinct. So we will use these integrated powers to look at trends over time in this talk. So here's an example, again, of 37 years or so of data from Albuquerque, New Mexico. You can see the Peterson noise corridor here that we use to reject non-noise power spectral densities. These are the Peterson low noise corridor models I described earlier. These are cal pulses, non-physical transients, way, way, way up here. This is station downtime, way down here. And all these things up here, almost all of which are colored, are earthquakes. And those are identified earthquakes, and the colored circles indicate power spectral densities that were removed. It's actually less than 10% of the data, but because there's so many data points, these colored ones overlap all the black data points here. And you can see 2 magnitude 9 earthquakes here, for instance, Sumatra and Tohoku, and their aftershocks where data were removed based on the ComCat catalog. Then we can take median smooth measures of these data to look at seasonal and interannual variation. So this, for example, is a 2-month moving median of these data, and you can immediately see the annual cyclicity due to Northern Hemisphere extratropical cyclonic storms, Northern Hemisphere summer lulls, and so forth in the data. This is, again, primary band. So this is the sum of the powers from the power spectral densities between about 14 and 20 seconds. So these are the basic data that we work with. And here's an example of what the whole thing looks like and at Albuquerque, New Mexico for almost 37 years. So here is all of the data in 61-day medians. You see the annual cycles here, and you can start to see with the L1 norm fitting trend, a hint of a significant trend here. Here it is when we remove the earthquakes. The scale's changed a little bit here, but it's almost unchanged. So even though there are a lot of earthquakes in 37 years, and we use a conservative data culling mechanism, doesn't affect the data that much. And similarly, this is a high uptime station, removing the Peterson model artifacts of exceptionally low, exceptionally high signal power spectral densities has almost no effect. And you see that in the trends here. They're basically the same. Then we do a Fourier best fit for this annual stationary cyclicity, and we remove it and we fit it again. And again, we get almost the same trend, but because the variance is much reduced by removing this, the 1 sigma uncertainty reduces. So ANMO has a highly significant increase of about 0.37% per year in vertical acceleration amplitude across the entire record. And here are some others I'll go through quickly. Here's Puerto Rico. It's got a very similar trend of about 0.38% per year. That's the bottom here. And we get percent per year by just normalizing the absolute by the median value. The actual absolute change is about 0.011 nanometers per second squared per year. This is Iceland, an exceptionally volatile and high energy station. It's changing by about 0.43% per year. This is Taiwan. This is an example of a station in the Western Pacific that has a negligible trend. And Palmer Station, Antarctica, the highest energy station in the world, sitting out there in the Drake Passage off of Antarctica. It's increasing by about 0.36% per year. So you might suspect that there's a trend here. And so once we started looking at some of these initial stations, we went through and evaluated all of the stations in this Nature Communications paper we published last November. And we just chose stations that had 20 years or more of data and 80% data completeness. This study that was published last year went through August of 2022. Of course, we can update this now that we've got a methodology on a daily basis. And there are 52 stations that met these criteria, and you see them here. Here's where they live on the map. So it's a good global coverage, not quite as good as we'd like. The size of these green dots indicates the median energy. So you see how more intense the primary microseism in this case is in the Southern Ocean than in the North Atlantic, for instance. So once we apply the methodology I just described to all of these 52 stations, you really see a remarkably consistent trend in primary microseism intensification around the world. First of all, 41 out of 52, 79% are positive at 3 sigma significant. About 8 of 52, or about 15%, are negative. The 7 most rapidly increasing primary microseism levels in absolute sense are in the Southern Ocean and North America. So that's the red box there. If we normalize them by their medians to get the percent per year change, the 7 most rapidly proportionally increasing stations are all in the Northern Hemisphere Atlantic. That's this box here. And they're increasing at rates that are roughly equivalent to what the oceanographic estimates are, again, about 0.4 to 0.5% per year. So this is what they look like if you plot the median component amplitude. This is vertical acceleration for all these stations. The most energetic stations in the world are Pitcairn Island and Palmer in Antarctica again. And these are sorted by various geographic regions as they were in the 2023 paper. But basically, you can see there are a lot more of them above this line that are increasing proportionally. This is the trend. So this is the rate of increase normalized by the median. Then there are on the negative side. So there's Palmer Station again, the most rapidly increasing in the world in the absolute sense. But once you normalize it by its median, some of these red stations up here in the North Atlantic region are actually increasing proportionally more rapidly than Palmer Station. And these are all those fast increasing stations. So this is what it looks like on a map. So we found that stations with these significantly increasing trends are widely distributed. They correlate geographically. The positive trends are particularly evident in the northeastern Atlantic. You see these very large red circles. This is the absolute acceleration. This is the absolute acceleration normalized by the long-term median. This is 0.5% per year. So you see that these rates of increase in the North Atlantic are very large, as are some of the increases in the Southern Ocean. There are a few stations that have significant decreasing trends. Two are in North America, Tucson and Hockley, Texas. I have suspicions that this may be a metadata issue. But then there's another trend in the Northern Pacific and parts of the Western Pacific that's much more geographically corroborative, and I believe that is actually a real trend that represents a net trend decrease, but only in that part of the world. The whole rest of the world is essentially increasing. So this is the energy result. So this is basically doing trend fitting to the velocity squared vertical component at all these stations. And this enables us to get a global wave increase average as sampled by the available stations. And for all stations, the energy is increasing at about 0.27% per year, global average. If I do a trend fit that starts at 1 January 2000, there's, with some significance, you could say that the trend has increased, as it has also increased with in some of the oceanographic studies, but the measurement of that inflection point or acceleration is still not of high significance. Again, these trends are comparable to those estimated by the oceanographers. And the greatest proportional increases are at Standing Stone, Pennsylvania. That's this one, SSPA, which is sensitive to Northern Atlantic climate. And RSSD, which, although it's pretty far west, actually also picks up a lot of energy from the Atlantic Ocean, which is propagating through the Canadian Shield here. And those are increasing on average over this data set by about 0.8% per year. So a few more comments on the primary mechanism. Again, it's caused by the direct excitation of long period, in this case, Rayleigh waves, since we're using the vertical component, from ocean wave dynamic pressure tractions acting on seafloor bathymetry. Because these dynamic pressures of waves decay to about they decay by 0.95 by about half a wavelength for 14 to 20-second period waves. This corresponds to ocean depths that are shallow, as we mentioned before, less than 150 to maximum of 300 meters. And that's only about 11% of the global ocean seafloor. So we can actually localize the primary just based on bathymetry pretty well to the near coastal regions around the world, or quite well. And all those essentially lie near continental and island coasts, with a very few exceptions. So primary microseism, because it's both simpler than the secondary and because it's this direct effect of bathymetry near the coast interacting with the waves, is actually a really robust proxy for the integrated wave forces of these ocean swell periods across Earth's coast. And on the right, you see a really nice study that was done by Gualtieri et al. That actually was able to use the primary mechanism as we understand it now and track it to the ocean coasts and actually model the amplitudes pretty well across the latitude. So we think we understand the primary mechanism pretty well. It still requires further refinement, and we hope to be doing that this year and next year. So another really interesting thing about these signals is if you smooth them over very long time periods, you can pull out the effects of El Nino southern oscillation variation in Earth's climate quite clearly in the wave climate as sensed by the primary microseism. So this is fairly complex figure from the paper I mentioned earlier. But I'll draw your attention to the Southwest Pacific here, and these are stations, individual stations, the Southwest Pacific. This is actually the El Nino Southern Oscillation Index, smoothed with a 3-year moving median, and you can see the correlation here. You can also see it's near inverse. The Southern Oscillation Index correlates quite well with wave intensity in the Southeastern Pacific. And again, if you take all of these 51 stations and you calculate their median, you get this increasing trend, but it also has significant oscillations. And these A, B, C, D, E events here are all ENSO events, either La Niñas or El Niños, that move the wave energy around from one side of the Pacific to the other on average, but both El Nino and La Niña increase the wave energy. This figure on the right shows the correlation of the bi-monthly 61-day smooth time histories between all of these 51 stations with station separation. And this gives you an empirical measure of just how spatially extensive this signal is from the ocean. You see it's quite spatially extensive indeed. We'll see that in more detail in a moment. I'll blow up that figure. So we can correlate these into groups based on their histories, and this just shows dendrogram analysis of that. And these are basically clusters of stations that have similar histories in their primary microseism. You see that they correlate very well geographically. There's a very distinct Northern Europe region, for instance, or broad European region. And this actually correlates very well with the study I mentioned earlier that used ocean wave data and the primary mechanism to simulate the stimulation of primary microseism energy. And you see that these groupings of source sensitivities for various stations, these are mostly geoscope stations, so they're different stations than were primarily used here, which are mostly GSN stations. The correspondence is quite good here in terms of the regionalization and the long-term reach of the primary microseism process, which extends over many tens of degrees of distance. So what about the secondary microseism? There's been a lot more work done on the secondary microseism. After all, it's the strongest long period noise source on Earth. And as I mentioned before, however, its generation is appreciably more complex. So although it's much larger, it's been studied much more extensively, it does have additional considerations that have to be satisfied for its strong excitation. Most fundamentally, it requires interfering ocean wave field components. They can either come from a single moving storm interfering with itself. They can come from a swell generated by a storm interfering with its reflections off of a coast. Or they can be generated from a wave field generated by two distinct storms that overlap and interfere and create these standing wave patterns that fundamentally generate the secondary process. In addition, the secondary process, because it creates a non-decaying pressure field that goes all the way to the open floor, is also sensitive to resonances in the ocean column of the acoustic waves that are propagating up and down through the column. And thus it has a more complex relationship to ocean depth than the primary. Primary only requires onshore waves. The secondary, of course, again, requires these interfering waves. And therefore, even when you have very large waves, you don't necessarily have a large secondary microseism because if it's not interfering with another wave field, it will not generate the requisite pressure variations to produce a large secondary. So the primary is a more reliable indicator of large wave amplitudes in the absence of other things going on in the ocean. So if you take the analysis I described earlier and apply it straightforwardly to the secondary, First of all, here's the primary trends I showed you earlier. You see the effect of removing the harmonics here. The error bars get smaller, but the trends are generally consistent when you remove the seasonal cyclicity and do the fit. These are the secondary microseism trends sorted in the same station order. And ones that are both positive, I've indicated as red. Ones that are both ones that are negative, I've indicated as blue, and ones that are non-determinative, I've indicated in gray. So if you plot those together, this is the primary trend in percent per year, the secondary trend percent per year. You see they basically do track pretty well, but there's a lot of additional noise here. And most of that is due to the fickleness, I think, of the secondary excitation mechanism. But nevertheless, they do come pretty close to a one-to-one trend generally. This is the same thing without normalizing by the median. So this is the secondary trend and the primary trend in an absolute sense. Of course, secondary is much larger, so these numbers are much larger than this. But again, you see a general correlation with some outliers here. But when you take a station like Borg in Iceland and you normalize it by its median, it actually falls back on the trend. So this is the correlation between all of these stations in the primary microseism. Yellow is 1. This is a station history correlated with itself. And this is the secondary. You see that generally these correlation pixels are smaller between stations for the secondary, which argues that they're more spatially variable. And that's correct. This is the figure I showed you before in red of the interstation correlation history of the primary, smoothed by 2 months. And this is the secondary. So again, you see the secondary is much more localized. It falls off much more rapidly with interstation distance. This is correlation from 1 to negative correlation. So clearly there's greater station specificity and more variation, and that's verified empirically by more rapid decorrelation of the station amplitude histories as you move the stations further apart. So you can look at this in more detail and try to figure out just what's going on in the secondary band that's different than the primary by looking at the signals themselves. So here are the primary period bands, the longer ones at Albuquerque, New Mexico. Here are the shorter secondary bands. And you'll notice that the trend estimate at 7 seconds is statistically much different than the trends at all the other periods, which are, fairly consistent around 0.35% per year. But something else is happening at 7 seconds. So this one is anomalous. And basically what you see generally when you do these analyses at various stations is that the primary trends, this is the trend in amplitude increase percent per year, is fairly consistent across the primary, but it shows large variations in the secondary. And if you look at the coefficient of variation for these time series, which is just the time series standard deviation normalized by its mean, you see that these coefficients of variation in orange here get much larger in the secondary band than they are in the primary band. That's just a sign of a more volatile time series at these shorter secondary periods. Again, that's consistent with the fact that the strong excitation of the secondary is a more fickle process. And this is, for example, the large El Nino La Nina event of 97-2000, where you see that these the variation, the secondary gets very large indeed in some of these period bands. Again, it's that increased coefficient of variation. And these are some additional stations that show something very similar. Again, you see the primary is has a low coefficient of variation. It's more consistent than the secondary, which shows a much larger variation in its time series. So you can do this at a much finer scale as you'd expect. So here's smoothing at 3.5-day intervals at ANMO. You still get, when you do the fit of the entire time series, almost the same trend. You can remove all these harmonics, and you can plot the outliers to look at extreme microseism events. Now, there's no magnitude or intensity scale for these wave energy transients, but we're working on a definition for that now. And one thing you can do with these is you can look at the top, say 1%, the extreme high energy microseism, and in the case of the primary band, this is long period, high energy wave events. This is Albuquerque, New Mexico. So these are primarily on the Pacific coast. And you can actually look at the annual count of extreme wave events with 3.5-day resolution, and you can track how they may be increasing secularly with time. So this is a direct measurement of long period swell, high energy events affecting mostly the west coast of the United States. There's a lot more phenomenology to explore as well. There's the relationship between the primary and the secondary, which is really interesting and has all these quite interesting trends at different stations. So this is the secondary median normalized amplitude on the y-axis of all these plots, and the primary median normalized amplitude on the horizontal axis at all these stations here. And you can see lots of interesting effects, as you might expect, but they're very systematic. So here we see saturation in Albuquerque, New Mexico, in Hawaii, in the Northern Hemisphere winter. So when we get these very large events, we tend to get more primary excitation relative to the secondary. This is the harmonic trend fit that creates these sort of Lissajous-like figures, and these are the individual time samples to show you how it looks. The calendar time goes from January to January, so these colors are Northern Hemisphere winter. These are Southern Hemisphere winter or Northern Hemisphere summer. But in New Zealand, you see something different. You see the flip in the seasonal polarity, of course, so Southern Hemisphere winter is up here. But you also see that the secondary increases more than the primary during high wave events. In Antarctica, you see the effect of sea ice, so that creates this counterclockwise cyclicity. As sea ice is minimum here, you see a trend like this, but when sea ice gets large, it attenuates the primary more than the secondary. So the annual cyclicity tends to look like this. And that's what you'd expect, since it pushes the large waves further away from the coast, where the primary mechanism becomes less efficient. Here's a more complex situation where you see probably bihemispheric influences here in Thailand. So you can see Southern Hemisphere and Northern Hemisphere waves at some of these low latitude stations. And then in the Pacific, there are stations, and I don't understand this yet, but we're working on it, that actually have a clockwise annual cyclicity, such as Rarotonga and Pitcairn Island looks like this as well. So hopefully I've convinced you, if nothing else, that seismographic data actually contain a lot of unique and very extensive spatiotemporal information on the changing state of the world's oceans. You can directly see the intensification that's been attributed to climate change. And there are a lot of other individuals, as I've mentioned, working in this area around the world, doing very interesting work related to the microseism and climate implications. Here's a paper I'll give a shout out for by Peter Bremerski, where he actually went back into the analog record and calculated extreme wave heights for the coast of California, going back almost 90 years, and showing that, since the 1960s, there's been this general intensification that does not exist in the previous record. Here's the paper that we published last year that summarizes many of the things that I skipped over relatively quickly. in this paper. But the point I want to make here is there's lots of interesting work going on here with lots of individuals, and the record is just getting more and more extensive. So in summary, I'd say that the primary microseism in particular is a very effective proxy for global coastal energy near the coast in particular. We can see the secular increase at 3 sigma at most GSN stations, about 80%. We can calculate energy increases across various time periods that are comparable, a few tenths of a percent, 0.2 to 0.3 for this interval, that are in the exact ballpark of what meteorologists and oceanographers have estimated. We've demonstrated that the primary in particular, but also the secondary microseism are remarkable spatial averagers. So they average over entire oceans or large portions of oceans. So they provide a really remarkable long-term proxy for large-scale energy changes in the oceans. We can very clearly see El Nino and La Nina cycles affecting the Pacific and global energy intensities. The secondary amplitudes and energies are largely corroborative with the primary, but have much more complexity. And we're starting to look at extreme events and other metrics that we can pull out of these data. So hopefully I've convinced you there are lots of interesting reasons to study Earth's ocean microseism. So with that, I'll put in one more plug for the 2025 Denver Environmental Seismology Topical Meeting of SSA. And thank you very much for listening.
Thanks so much, Rick. Fantastic presentation, very interesting topic, and just very thoroughly presented. If there are questions, please do type those into the Q&A box, and I'd be happy to read those aloud to Rick. For now, I'll go ahead and ask a question first. In this, you were doing a trend over the course of the full station history. Have you tried looking at trends in maybe decadal sections of that? And is there a difference in that kind of result?
Yeah, no, it's a great question. And again, in the paper I mentioned, we did estimate the trends since January 1, 2000, and they were generally higher, but there's a lot of noise in those data. So one reason it took so long to produce a paper like this is that, certainly 15 and even 10 years ago, it was difficult to start to pull these signals out. But actually, with the intensification of various climate effects that affect world storms, the signals really become completely unambiguous when you include the last 10 years of data. So as the data records get longer, we'll be able to either fit trends for specific periods of interest, or we'll be able to fit more complex functions to these data to try to get a better idea of what's happening across the world's oceans. But as you see, there's a lot of variation in these time series. So to really unambiguously pull out trends, you still need multi-decadal data.
Yeah, I can see that.
There's so much else going on.
Yeah.
In the weather.
With that in mind, though, our shorter term stations that you can do maybe a shorter look into that and see if those populations still end up in the same populations you've divvied up globally.
Indeed. And the project that I'll be pursuing with Frederick Simons this year will start to look at stations with basically 10 or more years of data. So we expect to increase the size of the station population that we're looking at by almost a factor of 4 in the next stage of analysis.
Exciting. Look forward to seeing those results. All right, we've got a question here from David Simpson. What interactions have you had with the climate community, and can you identify ways in which these results have influenced their research?
Yeah, that's a good question. That's a very large community of oceanographers, and I think, quite frankly, I mean, we're still producing sort of corroborations of things that they have been studying. However, I'm on my sabbatical this year at Princeton. Frederick Simons and I will be working on making those connections and working with colleagues in Europe who are also making connections in this area. And I think eventually, it's my hope that seismology will be a complementary asset to the integrated interpretation of these data, because they do have unique qualities that I think are still not fully appreciated by the broader climate community. One, of course, is the length or the potential length of record. The other is that we have wave period dependent observations that are hard to get at with other methods. And we have long-term continuous data on wave state. So I think it's still an effort for us to reach out to that community and build stronger collaborations, but it's certainly a goal of my upcoming sabbatical year to try to foster tighter communications. And ultimately, this should be jointly interpreted with other data to get perspective and retrospective estimates of the detailed wave climate. And the last thing I'll mention is that these metrics have unusually large scale sensitivity kernels, as I mentioned, and that enables us to potentially pull out smaller global trends that are more difficult to resolve in less spatially extensive measurements from the climate community. But it's still a work in progress for seismology, I think, to really get its seat or potential seat at the table in such things.
Great. I've got a comment here from John Orchid. He says, we, Berger, Lasky, and myself have built 3 new very broadband ocean bottom seismometers with a lifetime of 3 years and near real-time telemetry. Not only triaxial motion, but also a differential pressure gauge with bandwidth of millihertz to 4 hertz. This would also allow monitoring of edge waves, and this should potentially add to the climate program.
Yeah, that's great to hear. I mean, measurements in the ocean and in the ocean column from OBSs and floating platforms like the Mermaid system, I think are going to be really, really helpful in better characterizing what's going on in terms of both the primary and the secondary microseism process.
Certainly. All right, another question here from Sabine John. Can you comment about the difference in trends across different frequency bands? Do you think they illuminate wave properties in different parts of the ocean?
Yeah, that's a great question. I think, again, going back to the primary mechanism, that's a target of current research, is to see how systematic they are. And Frederick Simons and I are planning to reconstitute the Gualtieri et al. Primary microseism modeling code to really start to look at this and see if we can attribute this to different regions of bathymetry that relate to wave period. Again, the situation with the secondary is a lot more complicated because you can get booming sources in fairly deep ocean that aren't associated with the coast, that are dependent on exactly where and when interfering wave trains are interacting in the open ocean. So that's a more difficult prospect to fully understand the source region variation and the period variation in the secondary. But I know there are individuals like Fabrice Ardouin who are working on that now.
All right, I don't see any coming in. I have another one I had here. How important is the continuity of the instrumentation at these stations? As some of this instrumentation has gotten older, it has been needed to be replaced. Are these things you've seen within your data and have been able to account for them? Do you have any concerns about future upgrades?
Yeah, great point. I mean, this really this reinforces the extreme importance of station maintenance and accurate metadata to do these sorts of studies. I mean, the changes here, I mean, we're resolving trends on the order of 1/100th of a nanometer per year, effectively, at these stations, accrued over many decades. So the importance of station maintenance and accurate metadata it can't be understated for these types of studies. And it's really important, of course, when an instrument is changed, such as a new generation of very broadband seismometers implemented at these stations, that we pay particularly tight attention to making sure that the new metadata is functionally consistent with the old metadata. And that gets back to the advantage of using something like the microseism, among other methods, because we can immediately see steps in these data if there's a step in the metadata that's inconsistent with what the ground motion is doing. So one aspect of the work that we'll be doing in the future is to work with the network operators to identify possible metadata steps and other things that can be identified as instrumentation is changed, or retrospectively in the instrumentation record.
Excellent, thank you. Well, with that, I think we'll go ahead and conclude this webinar. So thank you again, Rick, for taking the time to share this work with us, and we look forward to the future.
Thank you. Thank you, everybody.